Good morning, ladies and gentlemen. In my last class, I have talked about the basic principle of working of the Inertial Navigation System, or in short known as the INS, wherein the accelerometers were used to find out the acceleration, which when integrated will give you the velocity, and on further integration will give you the displacement of that aircraft from the initial or the starting point. If you are watching this channel for the first time, or if you happen to missed out the last class, I will give the link on the comment. Now let's move on further from that. The accelerometer measures the acceleration on the direction in which it is aligned. So let us assume that this is the starting point. The coordinates and the altitude of that point is known to you already. Whenever you park an aircraft at the parking bay, okay, the coordinate along with the elevation is written right in front of the cockpit where the aircraft is parked. So you know the position of the aircraft and the altitude of the aircraft. Now I will require 3 accelerometers, okay, one along the east and the west direction, and another along the north south direction, and the third one in the z axis, that is the vertical axis. So the accelerometer, which is aligned in the east-west direction, will measure the acceleration along the east-west direction, which when integrated will give you the velocity along this direction, and when further integration will give you the displacement along the east-west direction. So now, once I know the displacement along the east-west direction, I can find out the change in the longitude, or chlong, C-H-L-O-N-G, or D long, from the starting position. That is, by how many longitude you have crossed. Similarly, the accelerometer, which is aligned in the north-south direction, will measure the acceleration in the north-south direction, the velocity and the displacement on the north-south direction, and you will be able to find out, the computer will be able to find out the change in the latitude, or CHLAT, or difference in latitude, or the difference in latitude, that is the lat. So now I know the starting coordinate, I know the change in the longitude, I know the change in the latitude. So if I plot it, I will be able to plot the position of the aircraft on a surface of the earth. And the accelerometer, which is aligned in the vertical axis, will be able to tell you the displacement along the vertical axis, that is nothing but the change in the altitude of the aircraft. So this is how the accelerometer is used to find out the position and the change in the altitude of the aircraft. But as we know that the aircraft always maneuvers. It pitches up, down, it rolls, bank, roll, and it also yaws. So therefore, these gyros, which were initially aligned along the east-west direction, or the north-south direction, or the vertical axis, will be displaced from the direction in which I need them to be aligned with. So these accelerometers need to be placed on a platform which is gyro stabilized. We know that a gyro, because of the first law of gyrodynamics, will try to maintain in that direction in which it is aligned. Now let's see that. Let's assume that the pen which is on my hand is the gyro axis on which the accelerometer is been mounted. Okay. Now the aircraft turns left, right. Okay. Even though the aircraft turns left, right, because of the rigidity of the gyro, this platform where the accelerometer is mounted will remain pointed in one particular direction. So even if the aircraft carries out the maneuver, these gyros will continue aligning on their respective direction which was intended for. So this stabilization of the platform can be done by using the conventional gyro, that rate integrating gyro or by means of a ring laser gyro. In today's class, I'll be talking about the working of a conventional rate integrating gyro, and further in my next class, I will be talking about the ring laser gyro and how by using these gyros we stabilize the platform so that the accelerometer keeps aligned with the intended direction in an INS. So now we will talk about the simple rate integrating gyro, wherein there is a gyroscope here, and let's say that this is the spin direction of the spin of the rotor. This is mounted on a can, so the can is directly in touch with the rotor axis, so therefore this can will act like a gimbal, and that too an inner gimbal. This can is pivoted at the another can, which is what is the outer can, and it is pivoted in this. So this inner can is free to rotate like this, right? The inner can will be free to rotate like this. So now there will be some weight onto this can. It is supported by this pivot. However, what we are going to do is we are going to fill up this space which is in between the inner and the outer can with a viscous liquid. Okay, since it is kept on a suspended on a viscous liquid, there will be less amount of weight which will be acting onto the pivot. So therefore the friction is also going to be reduced. It's some kind of a viscous liquid, means it's some kind of a oil. The axis where the spin axis lies is what we call it as the X and the X dash axis. And the direction in which it is 90 degree to the spin axis is what we call it as a Y and the Y dash axis. And the direction which is in the vertical axis is what we call it as a Z and the Z dash axis. Right? Okay. What will happen if I turn this can like this? If I turn the outer can which is attached to the aircraft frame, okay, the outer can will turn, but the inner can is not going to turn because it is free to rotate inside this. Am I right? So the outer can will turn, but the thing is the inner can will not turn because it is pivoted, it is free to move. So there will be no force which is transmitted onto the gyro. No force will be transmitted onto the gyro. Right? Similarly, if I turn this through the x-axis, the whole can will turn, both the can will turn, the inner as well as the outer can will turn, but however no force will be transmitted onto the gyro, basically because I am turning along with the spin axis. Isn't it? So there will be no force which will be transmitted onto the gyro. But now if I turn in the YY dash axis, similarly the can is gonna turn like this. Isn't it? If the can is going to turn like this, now what is happening? There is a force which this axis will come up, this axis will go down. Am I right? So that is, I am transferring as a force. I am transferring a force into the gyro in this direction if I rotate this can like this. So since the force is being transferred onto the gyroscope, this Y and the Y dash axis will be known as the input axis. Okay? Because any change in this axis, with that amount of force which is applied will be transferred to the gyroscope. So now if I make this gyro, if I make this gyro spin axis align with the aircraft nose. Let's say this is the nose of the aircraft and this is the tail of the aircraft. Any pitch up and the pitch down motion which I do, what is going to happen? The force is going to be transferred to the gyroscope because I am moving in this, rotating in this input axis. Similarly, if I align this rotor axis along the lateral axis of the aircraft, this is the nose and this is the tail and this becomes the lateral axis, right? If I align this gyro spin axis in the lateral axis, anytime I put a bank, I put a roll, when I do the roll, the force will be transferred to the gyroscope and the gyroscope will precess. So that's why it is known as the, since the force is transmitting, it is known as the input axis. Let us see what happens if I apply a force onto this gyro. Okay, if I am turning the YY dash axis, let's say clockwise like this, I am applying a force here. And this is the direction of rotation of the gyroscope, right? So therefore, what will happen? It will be transferred, this force will be transferred by 90 degrees and it will be equivalent to applying a force here. If the force is applied here, what will happen? This inner can will start turning in the ZZ axis. In this case, it will start turning like this, anti-clockwise. The speed at which it is gonna turn, rotate in the ZZ dash axis will be directly proportional to the amount of force which is applied at the YY dash axis. Now, let me demonstrate it. This is the rotor of a gyro. Okay, and this is the rotor and this is the spin axis. Okay, this is the rotor and this is the spin axis. So it will be there also. Like gyro, let us assume that gyro is rotating like this. Am I right? Where is the input axis? The input axis is this, right? So anytime, and this is mounted in the can like this, am I right? Inside. Anytime I put a turn in this way or this way, the force is going to be applied onto the gyroscope like this or like this. Am I right? If I apply a force like this on a gyro and the gyro is spinning like this, this force will be carried forward by 90 degrees and it will be as good as applying the force here. Isn't it? And the gyro axis will turn like this. So therefore the inner can will start rotating. And the rate at which the gyroscope is turning, precessing, will depend upon the amount of force I am applying, right? Isn't it? More the bank, more will be the turn. So can I derive a relationship between the rate at which I am applying the force and the rate at which the gyro is turning? So now I know that whenever force is applied, gyro will start precessing or start rotating. This rate of rotation can be picked up by the pickup coil and it can be amplified to drive a motor. So now because of the different maneuvers which are carried out by the aircraft, if any particular gyro or that platform is displaced from the initial position, the amount of displacement from the initial position or the initial alignment can now be determined by the help of this gyro, and that platform can be driven back to their initial position. So this is the use of the rate integrating gyro in an INS to stabilize the platform. This stabilization can also be done by the ring laser gyro. The working principle of the ring laser gyro will be discussed in my next class. Thank you, ladies and gentlemen. Once again, if you are watching this series for the first time, then I request you to kindly watch my previous video on INS so that you'll be able to place yourself comfortably. And thank you for supporting me on this channel. I would request you to kindly like, subscribe and share it amongst your friends so that it motivates me and helps me to bring you more and more videos on aviation. Thank you, ladies and gentlemen.